All right, so this is graphing rational functions. Now we're going to have some nonlinear parts. All right, we're going to have some exponents. Right? Maybe we'll have something to the second power. Maybe we'll have something to the third power. All right, so we started with where we had the first two here, where we had k over x, which is a parent function. K is a constant. And we have just a variable in the denominator. And our vertical asymptote was x equals 0, because you can't plug in 0, because it makes our denominator 0. Horizontal asymptote is y equals 0, and that's because there's no way k can equal 0. It's a constant number. And then we jumped up to the second one here. So this was the first one we looked at. This was the second one, and we kind of looked at those together, because it's the same basic graph, just shifted around. Right? So if we add or subtract something to x, it's going to change our vertical asymptote. So now x equals b would be our vertical asymptote. If that was x plus b, it would be x equals negative b as a vertical asymptote. And if we add something to the whole function, k still can't equal 0 because it's a constant. But if we add something to the whole function, it's going to shift it up or down depending on what the value of the number is. And so y equals c becomes our horizontal asymptote. All right, and then we saw the ones where we had an x in the numerator and x in the denominator. So we have ax plus b over cx plus d. Our vertical asymptote, we set our denominator equal to 0. So if we set cx plus d equal to 0, we'd have cx equals negative d. And if we divide by c, x is negative dc. That would be our vertical asymptote. Our horizontal asymptote is going to be the ratio of those coefficients. Right? So a over c. Right? And so, but rational functions can include nonlinear parts as well. So now instead of just an x in the denominator, we have an x squared minus 9. Right? So a little bit more involved. So a rational function, r of x equals p of x divided by q of x in lowest terms, will have a vertical asymptote, x equals r, if x minus r is a factor of the denominator. A rational function has no vertical asymptote if the denominator or all of its factors can never be equal to 0. We saw one like that when we had an x squared plus 1, right, in the denominator when we first started this lessons. If a rational function has no vertical asymptotes or points of discontinuity, it is a continuous function. Right? So if it doesn't have any asymptotes and doesn't have any breaks in the graph, it's a continuous function. A function is continuous if you can draw the graph without lifting your pencil. A point of discontinuity occurs when there is a break in the graph. Ones we've seen so far are called infinite discontinuities. Right? There's vertical asymptotes. They call it infinite because it goes on forever. Right? We have another type of discontinuity that we'll see in a later lesson, and that's called a point discontinuity. A point discontinuity is basically, whoops, wrong hole. I was about to spell hole with a W. That would be the wrong hole. Is basically a hole in the graph. We'll see those in a later lesson. So we're going to do some domain again. So remember, the domain of a rational function can be restricted. Let's see if I remember to erase from the last time. All right, so this has been factored for you. We want to find the domain of the following rational function. So we have r of x equals x plus 1 over x squared plus 8x plus 12. First, let's figure out the vertical asymptotes. So what's the vertical asymptotes? Orange 2. What's our vertical asymptotes? Uh-huh. Yeah, and make sure it's always x equals for vertical. X equals 6 and x equals negative 2 are the vertical asymptotes. How about, we'll write the domain over here where we have a little bit of space. The domain, anybody at blue? Uh-huh. Which number smaller? Negative 6. You're missing something. Negative 6, 2. Devin?
Negative 2.
Negative 2. And now you want to finish it up, Devin? Or you want to finish it up? Yeah, negative 2. No, we're doing infinity. All right, so they go in order from least to greatest. All right, so let me see if I can move that up a little bit. All right, so we have a break. We have a break for the first vertical asymptote, negative 6. Right? So we skip over that value. Can't use negative 6. It makes our denominator 0. And then we're fine until we get to negative 2. And we have to skip over that value as well because we'll have a 0 in the denominator. And then we're good from negative 2 to infinity. So it's all real numbers except negative 6, negative 2, and we're going to write them in interval notation. Let's do another one. All right, so what are the vertical asymptotes for this graph? Purple 1. You knew it without him helping you. X equals 4, x equals negative 4. How about the domain? Yellow 2. Yep, so we have a break at negative 4. So we go from negative infinity, that's supposed to be a 4 there. We go from negative infinity to negative 4. We have another break at 4, so we go to negative infinity to 4, and then 4 to infinity. That's our domain. And let's move the rest of the screen out of the way. Oops, there was one more. Oh, well. So the last one I'll just show you, right? Because x squared plus 9 can't possibly be equal to 0, right? If we set that equal to 0, there's nothing that makes it 0, right? So if I have x squared plus 9 equal to 0, and then I subtract 9, I have x squared equals negative 9. If I take the square root of both sides, we get x equals plus or minus 3i. And there's no complex numbers for the rational functions. So here, there would be no vertical asymptotes, right? We're going to stop here, and I'm going to put up the closing. So thanks for watching. Bye for now.